Hello everyone, I'm Xiaozhu, PhD student at the University of Michigan. Very happy to present our research on analyzing the first mile ingest performance of live video streaming, where we develop a novel measurement tool called Livelyzer and use it to study live video ingest performance. This is a joint work with my mentor Shubo-sun from AT&T Research and my advisor Molly Mo. Live streaming consists of the ingest and distribution paths. In the upstream ingest path, the video is captured in real time by a camera, then fed into a broadcasting app, which encodes the video and transmits it to a remote video server owned by some streaming service over an internet connection, typically cellular or Wi-Fi. On receiving the ingest stream, the video server transcodes it into a number of different adaptive bitrate or ABR tracks. Each track represents the original video, but at a different quality level, and consists of several video segments. On the downstream distribution path, viewers watch the live stream using players on different platforms, which request a mixture of the segments from the video server based on the downstream network bandwidth evolution, and this is called HTTP adaptive streaming. The first mile ingest path is likely to be bandwidth constrained with time-varying capacity, making the task of high-quality video delivery challenging. Existing studies have largely focused on the last mile distribution path from the video server to the viewers. There has been little exploration of the first mile ingest path. However, this first mile is critical to the end-to-end performance of the pipeline. The quality of the video delivered on this first mile imposes an upper limit on the quality of the ABR tracks created from it, and therefore on the quality of the experience, or QoE, of the viewers of the live stream. In addition to deliver a good video quality, the first mile also needs to provide the content with low latency. However, achieving this goal is also challenging due to the usually more dynamic and limited wireless uplink resources such as cellular uplinks, as well as the complexity of the ingest path as I mentioned earlier. To shed more light on this critical live streaming component, we need to first have an in-depth understanding of existing designs, characterize their performances, and identify spaces for improvement. This is beneficial for a wide range of entities such as network operators, testing services, as well as application developers. Understanding the first mile ingest path is not trivial. Even the ingest path itself involves a complex pipeline. A broadcasting app captures a video from a camera, encodes it using a codec, and transmits it to the remote server. To cope with bandwidth variations, it may dynamically adjust the upstream transmission. Different services can have very different designs. Unlike the distribution path, where HTTP adaptive streaming is the predominant approach, there is no single de facto delivery solution on the ingest path. Besides, there are other challenges such as the proprietary closed-source software, the live nature of content making it hard to conduct repeatable experiments, as well as a lack of well-defined metrics to capture the performance of the ingest path. In view of these challenges, we built Livelyzer, a generalized active measurement framework for analyzing the ingest performance of live stream. Next, I will talk about its design. Commercial streaming services and broadcasting apps are usually closed systems. Hence, it is hard to access either the ingest endpoint of the video server to gain visibility into the uploaded frames, or the encoder of the broadcasting app to examine compressed frames. Given the lack of such internal visibility, we adopt a black box analysis approach. Specifically, we control both the video content and the network condition. We then observe the quality and timing of the created top ABR track. By changing the input and environment, we can observe how the output will be affected and reason about the ingest performance. More specifically, we design Livelyzer, a holistic measurement system that comprehensively examines the ingest performance of different broadcasting apps streaming to various services. It consists of the following components running on the test device and analysis server. In this video, I will focus on the major components highlighted in blue and introduce them one by one in detail. Let's start with the video source creation. To measure both frame loss and quality of the delivered video on the ingest path, we need to associate each frame in the received video with its corresponding frame in the source. Achieving frame alignment in live video ingest is challenging because the frames in the source and received videos are not naturally aligned. For instance, when there are frame drops, the first frame in the received video may not correspond to the first frame in the source. Besides, the identification is to be robust to scaling and compression-related quality distortion. To address these challenges, we overlay a unique signature to every source frame and leverage computer vision techniques to detect the signatures from frames in the received video to match each of them to a source frame. We leverage the QR code to create this specific signature. QR code is more robust than the approach of overlaying a sequence of digits due to its use of advanced error correction. We next look at the Livelyzer virtual camera. As mentioned earlier, we need to do measurements in a repeatable way. This means we need to provide the same video content to the same broadcasting app across different runs. One way to address this is to capture the same scene using a real camera. However, it's difficult, if not impossible, to keep the captured video the same due to lighting-related dynamics. Some broadcasting apps support local file input or screen sharing, but not every one of them supports these modes. Also, screen sharing introduces non-deterministic distortions in the screen recording process, making the video captured by a broadcasting app just an approximation of the source video. To provide a universal interface to commercial broadcasting apps for capturing repeatable video content, we create a virtual camera in Livelyzer. It takes a local video file as input and behaves like a normal video device from the perspective of a broadcasting app. The virtual video capture function extracts the sequence of frames from an input video file and redirects them to the broadcasting app. Livelyzer also runs a segment downloader, which collects video server output for performance analysis. To facilitate ingest performance analysis, we need to measure the quality and timing of the stream delivered to the video server. However, extracting video frames in such a stream on the ingest path is challenging. Instead, we use a transcoded top ABR track to approximate the above stream, which is easily accessible using standard HTTP APIs from the distribution path. The top ABR track is also more closely associated with end viewers' experience, as players ultimately need to fetch video segments from ABR tracks, and the top ABR track represents the best quality encoding any user can receive. After collecting the measurement data, the performance analyzer running on the analysis server will perform data analysis. As mentioned earlier, we need to define performance metrics on the ingest path that impact end-user QoE. We would first like to quantify the video quality. To this end, we examine the quality of video segments in the top ABR track created by the video server. For the specific video quality, we adopt VMAP, which is a recently proposed perceptual quality metric. We are also interested in measuring the extent of frame drops. For this, we define effective frame rate as the number of distinct frames in each second in the top ABR track. Besides, for live streaming, we are interested in understanding how far away we are behind the live event. We define the ingest delay for each ABR segment as the time elapsed from when its first frame is generated at the source to when all the ABR track LiDAR variants of that segment become available at the video server for players to download. Finally, we answer the question of the stream smoothness by measuring the store behavior due to segment availability time variability. So far, I have shown the key components of Livelyzer. More details can be found in our paper. Now that I have introduced the Livelyzer measurement system, I would like to demonstrate how we can use it for performance evaluation of popular live streaming systems such as YouTube, Twitch, and Facebook Live. Our ingest analysis focuses on two aspects: broadcasting apps encoding conducted under high network bandwidth scenarios to see what's the best it can do, broadcasting apps rate adaptation, where we explore more bandwidth-constrained situations and see how different apps react to them. In our paper, we also include results for server-side transcoding analysis. We use 3 different representative video contents as our broadcast sources, covering different scene complexity as characterized by their spatial information, or SI, as well as their temporal information, or TI, as shown in the plot. The broadcasting apps and streaming services we examine are shown in the table. As shown, we study 3 types of broadcasting apps: OBS, web, and mobile. OBS, or Open Broadcaster Software, is a popular third-party broadcasting app that supports video transmission to different services. Web means uploading live videos from the service's web page in a browser. Mobile means live video ingest from the service's mobile app on a device. The three commercial streaming services we examine are denoted as S1, S2, and S3. Let's first look at the broadcasting app encoding. We make two main observations. First, different broadcasting apps have very different outputs with different encoding bitrate distributions for encoding the same content, suggesting different encoding settings. We also find that many of them create encodings unaware of the video content, suggesting the use of a CBR encoding, which could potentially cause inefficient usage of the network bandwidth. Given that VBR has advantages over CBR in terms of encoding quality or bandwidth usage, one potential research direction is to explore using VBR encoding in broadcasting apps. Next, we study how different broadcasting apps adapt their upstream transmission to cope with network dynamics and the impact on performance. There can be different ways of adjusting the amount of data to send to the network, such as dropping frames or reducing encoding bit rates. We leverage the network condition emulation feature of Livelyzer to replace 6 real-world network bandwidth traces. For each of them, we create 3 variants for each broadcasting app by proportionally scaling the per second bandwidth values in a trace, such that the average bandwidth of the resulting scaled trace becomes a certain portion of the broadcasting app encoded bitrate measured under ideal network conditions in the previous slide. I will present the results for 2 rate adaptation designs, the default OBS adaptation and a more advanced design introduced by OBS recently. Results for other apps can be found in our paper. Let's start from the default OBS rate adaptation. The figure is about to show the quality of the video streaming from OBS to service S1 under the 18 different network conditions created by scaling 6 real bandwidth traces such that the average bandwidth of the resulting scaled trace becomes either 60%, 90%, or 120% of the average encoding bitrate. For comparison, we also show the baseline video quality under ideal network conditions. Overall, the Vmap values show significant degradation compared to the results without bandwidth constraints. We also observe similar results for S2 and S3, with around 30% Vmap drop on average, which is very significant. We conducted a root cause analysis of the largely degraded performance with details in our paper. Briefly speaking, the OBS broadcasting app, by default, drops frames in a very inefficient way in order to cope with network condition degradation. Starting with OBS version 24 back in 2019, dynamic bitrate mode was added as an optional scheme to replace the default rate adaptation scheme. We now study the performance of this new mode under the same network conditions. Overall, the video quality is improved compared to the default OBS rate adaptation. However, there are some scenarios where the quality becomes worse. To understand this new adaptation behavior, we measure the performance evolution across time and correlate it with the network bandwidth condition. The graph on the right shows an example run for this broadcast setting under a specific uplink condition. We find that the network resource frequently becomes underutilized. The remaining period, the bandwidth is higher than the baseline OBS encoding bitrate. However, the broadcasting app does not leverage the increased bandwidth to reach the maximum encoding bitrate. Instead, it always increases by a small fixed amount every 30 seconds, irrespective of the actual network bandwidth. As a result, the Vmap can stay low even after the network bandwidth rapidly improves. Our measurements showed a vast diversity of performances across different scenarios, suggesting different broadcasting apps and services choose different points in the design spaces. Next, we use Livelyzer to perform a what-if analysis and identify ways to improve the upstream ingest design. It is vital to deliver the content on the first mile at high quality with minimal impairments, as it becomes the source reference used for the ABR track encoding and downstream delivery to end users. However, the limited and varying bandwidth on the first mile make this task difficult, as shown by our characterization of existing designs earlier. Next, we conduct a what-if analysis to explore the potential of 2 techniques for improving the video quality on the first mile: suitable rate adaptation to better adapt to network conditions, and using more efficient codecs. In this talk, I will focus on the first direction. Details about the second one can be found in our paper. For ABR streaming, rate adaptation has been studied extensively on the distribution path. On the ingest path, there is a single variant being transmitted, Conceptually, an adaptation scheme that tailors the encoding bitrate to the actual network bandwidth variability should be able to deliver better QoE. However, there has been much less research on the beta adaptation for the live streaming ingest case. Previous slides show that while the existing broadcasting apps seem to have rate adaptation schemes built in, their performances could be further improved. To understand the potential improvements possible, we design a simple proof of concept scheme that better adapts to bandwidth changes. In every epoch, we compute a new encoding bitrate based on the predicted uplink bandwidth. The new bitrate is calculated as a function of beta, the predicted bandwidth. Eta is a tunable parameter introduced to control the aggressiveness of the adaptation algorithm in terms of bandwidth consumption, and the max bitrate is the maximum video encoding bitrate specified by the system or user. We implement this new adaptation logic in OBS, the open source broadcasting app. We compare it with the default OBS and OBS dynamic adaptation schemes. This figure shows the video quality associated with streaming from OBS to S1 under the 18 different network conditions described earlier for OBS. As shown, OBS Adapt noticeably improves the video quality across different network conditions. The average store ratio is also reduced by more than 20%. Note that OBS Adapt is not a full solution. We simply use it to evaluate the space of improvements possible beyond the current OBS adaptation schemes. To conclude, we explore the first-mile ingest aspect of live streaming. We developed Livelyzer, a generalized active measurement and black box testing framework for analyzing the performance of this component in popular live streaming software and services under controlled settings. We use Livelyzer to characterize the ingest behavior and performance of several live streaming platforms, identify design deficiencies that lead to poor performance, and propose best practice design recommendations to improve the same.